All right, let's get started with today's content. So today we're going to be talking about battery and system sizing. Hopefully this training can educate you on kind of how to put together the parts and pieces of a system, especially if you're a newer installer, and why maybe kind of an all-in-one system may be an advantage for you, but also how our product can be scaled and how it is versatile and able to meet your customers' needs as you grow in familiarity with the sizing process and system design. So it is a very scalable and versatile product that really can meet the needs of any system once you understand how to use it and how to modify it. So our batteries are used in a variety of applications, such as peak shaving, time of use, and integrated solar and storage. So peak shaving, if you're not familiar, this is reducing costly demand charges. Anytime you go over a certain amount of power used at any one time, even if it's not used for a long time, you will get charged quite a bit extra for that power. So it's just kind of a flat fee that occurs anytime you exceed that. What you can do is kind of interrupt your loads in between the grid and the loads. Adding the support of a battery and solar system there can help you shave off that peak power. Having the solar and battery system kick in anytime you're pulling more than a certain amount of power, using current sensors to actually sense how much power you're pulling from the grid, and then turning that system on anytime that value rises above your preset value. You can also use our systems for time of use rates. So a lot of customers, including myself, get charged quite a bit extra between the hours of 5 and 9 p.m. So I actually get charged up to 45 cents per kilowatt hour, depending on what time of day it is. And of course, integrated solar and storage, you can't really just use solar at your own house. I mean, sure, if you're producing during the day and you have a couple lights on, you're using your own power most likely, but for the most part, you're not really home. You're not really around when your system's producing, and you don't have control over where that power is going. It's just going back to the grid, and they're using it how they want. So integrating storage into your system gives you control over where that power is going. So we're going to look at a few application overviews today as far as system sizing goes. Methods for sizing equipment are going to definitely vary greatly depending on what application you're looking into for your customer. So are they grid connected? And if so, do they want to back up their entire home with battery energy storage, or just their critical loads, which is almost always the more cost-effective way to go? Are they off grid? Do they have wind, hydro, solar, or all three of those? And do they have a generator? That's another question that you're going to have to ask. Do they have an existing system? So are you replacing lead acid batteries and older inverters? Are you leaving the old inverters and just replacing the batteries, etc.? And even some lithium batteries are now, I mean, lithium batteries have not been popular for too long in the residential market, but there are some now. Some of the early adopter customers are ready for a replacement. So we're going to start out talking about backup power, and as this relates to whole home backup. So when you're backing up an entire house, usually the inverter is between the main loads panel and the critical loads panels. It's going to reside in between those, and you're going to move all of your loads over to the critical loads panel. So a smart load panel can really cut down on costs here. If you've got a 200 amp service, for example, that is a huge amount of power, and it's highly unlikely that you're ever really going to need all 200 amps at once. And instead of just creating an inverter and battery system that's capable of powering all 200 amps of your service, as you would do with a generator, instead of doing that, the much more budget-friendly option is to use a smart loads panel. So you're going to put your loads that you want backed up on that smart loads panel. The loads panel is going to allow you to power all the loads, but if you're ever drawing too much power or coming up onto, the limit of your inverter system, it's going to simply turn off loads in the order of the priority that you've marked them. So let's say that you really want to make sure your electric stove is always able to operate, mark that priority 1. Air conditioner, priority 2. Maybe the clothes washer and dryer, that's down further on the priority, like number 8 or 9 or 10. That's going to kick off first as soon as you butt up against that power demand maximum value that you've set in the software of the critical loads, or excuse me, the smart loads panel. So that's going to be a lot more budget friendly than sizing based on the peak demand. And you can also, well, you will have to also size based on the kilowatt hour energy consumption and the days of autonomy your customer wants. So days of autonomy basically means how many days do they want to survive a power outage with no charging capabilities. Now, if they've got a massive solar system and you've wired it in such a way that it's going to stay on during an outage, I wouldn't really worry about days of autonomy very much unless they live in a very, very cloudy place. I would just size for 1 or maybe 1.5 or even 2 days of autonomy at most. Remember, guys, storage is expensive, so you really want to size often the PV array larger and the battery system smaller if your customer wants to kind of survive off grid for a long time. You can look at the utility bill to determine their average daily kilowatt hour consumption. So that's pretty easy there. Or you can actually calculate it based on the kilowatt demand of the load and then multiply that by how many hours they'll be running the load, right? So kilowatts times hours is kilowatt hours, which is how you size a storage system. So these are just some home examples, right? Here we've got a smart loads panel controlling the loads here. So all the loads from this main panel have been moved over to the critical loads panel, and there's a smart loads panel kind of interrupting that as well. So let's do an example. Let's say a customer's utility bill shows 20 kilowatt hours per day of consumption on average with a 7 kilowatt peak demand. So they're never pulling more than 7 kilowatts, and they only want 1 day of autonomy. Now, we really would recommend sizing in most cases for 80% depth of discharge. In this case, however, if your customer's not cycling daily, they may really want to use more like 90 to 100% depth of discharge, and that's totally fine. So we'll call it 90% depth of discharge at 3.8 kilowatt hours using our Phi 3.8 battery, and that gives you about 3.4 kilowatt hours per battery that's usable capacity. So if they need 20 kilowatt hours, you're going to divide that by the usable capacity here and round up if there's a decimal. So you're going to need 6 batteries in this case scenario. Now, how about the inverter? With a 7 kilowatt peak demand, you can cover that with a solar converter. Got a good question coming up here. Why would you choose 90 to 100% depth of discharge if they were not cycling daily? That's a good question. So in my mind, it's a 10-year warranty flat with unlimited cycle life, and depth of discharge does not affect warranty. So realistically, if you are not cycling that battery system daily, you might as well get all your money's worth out of it and cycle it as deep as you can. There is some sort of a component to battery life as far as, how long they've just existed and sat on a shelf. So if you don't cycle that battery at all, it doesn't mean it's going to last 1,000 years. There is, value in actually just putting it to use as well. So if you're going to be cycling it daily at 100% depth of discharge, it's going to wear it down pretty quickly. But if you are going to be not cycling it daily, then using 100% depth of discharge is really not an issue in terms of wear and tear. So now let's say this same customer 2 years later is using 30 kilowatt hours a day. They've increased their consumption and they need a 9 kilowatt peak power demand. And this peak demand needs to be covered even when they're off grid. So they now want 2 days of autonomy at 30 kilowatt hours a day. That's 60 kilowatt hours total. And remembering that they need to account each battery as 3.4 kilowatt hours, can anyone tell me how many batteries they would need for this system? Got a couple of responses here. Perfect. 17 and a half. You're going to round that up to 18 batteries total. So 18 batteries needed. That's a major upsell. And the advantage here is with our 5 batteries, you can go back later down the road and add more to an existing system. So this is one example of what an 18 battery system could look like if they do need it outside. We've got our access cabinets that can contain the batteries, NEMA 3R rated, outdoor ready, and our boss cabinet, which is the same basic cabinet with batteries instead of an inverter on top. Let's talk about critical loads in terms of backup power. So a grid connected home that doesn't need a whole home backup, but just needs some most important loads backed up. It's really the same thing here. You're going to place several loads on a critical loads panel. However, your system should be capable of powering your critical loads indefinitely from renewables or a generator without the grid. This is the difference here, is you're not sizing for 1 day of autonomy or 10 days of autonomy. You need to be able to power those loads every day because they're critical loads. So no matter how long the power goes out, these loads need to stay on. We're talking about medical equipment and refrigerators here. This is, Wi-Fi routers, important stuff. So you're going to size based on both the kilowatt hour consumption of the loads and instantaneous peak demand. You got to make sure you exceed both of these needs. Usually, you're just going to size the renewables or generator to recharge the battery bank daily, as again, going back to this needs to be powered or at least be capable of being powered without the grid. So let's say your load calcs reveal an 8.5 kilowatt hour a day consumption, a 5 kilowatt peak demand from critical loads. You're going to size this PV system to recharge daily. So you only need that 8.5 kilowatt hours a day. But in this case, since you are cycling daily, like we talked about, we're going to go with 80% depth of discharge for sizing the battery system. And then we end up with about 3 kilowatt hours per 5 battery. This is going to be 2.8 batteries needed, and we're going to round up to 3. As far as the inverter, just make sure the inverter cannot draw more power than the batteries can provide. So at 5 kilowatt peak demand, you're totally okay with 3 batteries. They can provide 1.9 kilowatts each. So you're at 5.7 kilowatts continuous output with that 3 battery bank. Let's look at an example. Let's say you have a customer with AC coupled solar array existing and they want to go back and add storage and move some critical loads off of the main panel. It's really that easy. You're going to drop the access unit in the middle of the system such that it can disconnect from the grid and continue to power the other side of the system. So powering those critical loads and sending a grid signal to keep these AC coupled inverters alive. These are going to allow you to continue to produce solar in an outage. Oops, excuse me there. So going back, before you added this system, the customer, maybe they didn't even realize this, but their solar system is not going to continue to produce power in an outage. It's just going to turn off because it's a requirement and a safety feature that grid-tied inverters such as these cannot continue to produce power in an outage. They need to see the grid present in order to produce power. This is so they don't injure line workers from the utility company as they're messing with those lines, getting them back online and up and serviced. They don't want the lines to be energized. So adding this solar system not only gives the customer, adding this battery system and inverter system here not only gives the customer that battery storage, but it also gives them a lot more time that they can survive off grid because they've got this incoming charging source that they didn't have before. All right, so getting into a little more complicated stuff here, peak demand charges and time of use. So how do we avoid those charges and sometimes even use the time of use structure to our advantage as a customer? So for example, if you're getting charged more between 5 and 9 p.m., depending on where you are, your utility may also pay more for power that you sell to them during those times. So that's something to consider is, can you actually overproduce early in the day, store that up, and then push it all back to the grid between 5 and 9, save up those energy credits, and drain your batteries during that time, and then use energy from the grid overnight when it's very cheap. It's something that a lot of people are doing, but it depends where you are. Not every utility company or jurisdiction is allowing that kind of rate structure. Some are paying as little as 3 to 4 cents a kilowatt hour when they sell back, no matter what time of day. So again, peak demand charge, it's really something put in place by the utility. It's kind of when you go over some arbitrary amount of power usage at any one time, you're going to get charged a flat premium fee. So how can we use a battery bank to mitigate this? Is we can put current sensors on the wires that are bringing grid power into your house and cause the battery bank and inverter system to push power to the grid if ever the amount of power that you're buying from the grid is approaching that peak power charge. So this will push power to either the grid or the loads. Either way, it's kind of pushing the power to the same place so that you will buy less power from the grid. In most cases, DC coupled is really suggested for this due to the system's ability to easily self-consume power, right? When you're pushing power onto an AC bus bar, it's a little bit hard to understand where it's going. The solar panels just connecting to the same bus bar that the grid and the loads are on. It can be a little difficult sometimes for inverters to figure out where that power is coming from and where it's going. As far as sizing considerations, so think about how much power you're actually going to need. What's that delta there that you actually need the system to cover? If all your loads are turned on at once, especially in like a commercial industrial application, it's a little easier to add up those loads and just see what that actual delta is. Also, these are often going to be surges of power, a few seconds, a few minutes. Unlikely here to be more than multiple hours. So one thing to consider here is if you just need a 5-minute surge, our batteries do have quite a large surge capacity. We're talking 100 amps for 10 minutes on several of our battery models. So that's about 5 kilowatts per battery that you can surge for up to 10 minutes. If you just need a 5-10 minute surge, that is going to greatly assist you and reduce the overall size of your battery bank that you need to cover this delta here. Whereas if you do happen to need the delta, this amount of power covered for multiple hours, you're going to want quite a large battery bank to handle that. So, as an example, if the utility company charges 1.5 times the amount of normal rate for any power used over 50 kilowatts, and the customer has noted a max power consumption of 75 kilowatts, in this case, the battery bank needs to be capable of discharging at least 25 kilowatts to cover that delta. That delta there would be 25 kilowatts. This would then prevent the utility company from ever needing to supply power over 50 kW. So in this case, we would either need 14 or 7 batteries. It depends if your 25 kilowatt surge is for less than 10 minutes or if it's just multiple hours. So if it's less than 10 minutes, you can get away with 7 batteries here to cover that. If it's more than 10 minutes, you are going to need double the size battery bank. That's why it's important to understand how long you need that surge for. Any questions here? All right, so moving on to time of use arbitrage, how we can actually leverage time of use rates. So time of use rates are becoming extremely common. More and more utility companies are adopting them. There are definitely some who do not have them. Middle of the country, there are plenty of people I've talked to who simply told me, what are time of use rates? But me here in California, like I said, I'm paying about 45 cents on the peak hours. So what you can do is use a battery bank to supply power during this time. Again, here, going back to DC versus AC coupled, you're going to have more control over where the power is coming from and where it's going if your solar power and battery power is coming in on the DC side instead of having an AC coupled solar array. So sizing considerations here is, first off, find out how many hours, what's the time frame. And then there's 2 ways you can go about this. You can do load calculations as usual, or you can also often go to your utility company and they'll give you 15-minute data based on how much power you used during any 15-minute portion of the day. I have pulled these logs on my own property. It's eye-opening, to say the least, and it's kind of crazy to think how much data they actually give you. I mean, I was looking at a spreadsheet with thousands and thousands of columns of data. So, but it is easy if you know how to use Excel to just analyze that data in an automated way and figure out a decent average. And these time of use charges, right? It's not critical. It's not as critical as peak demand charges. It's not life ending if you end up having to pay for a couple of kilowatt hours here and there during the peak power time of day. You want to avoid it as much as possible, but 67 cents here or there, or in my case, 45 cents here or there, it's not going to break the bank. So you just want to get close enough in this scenario. Let's look at off-grid, my favorite application here. I find this to be the easiest way to size a system. So first off, if you're living off-grid, DC coupled is the most common. Now, the reason for this, I would check out our DC versus AC coupled training, but really, ultimately, it's more efficient. If you're off-grid, then there's no question that DC coupled is more efficient. There's less losses and less AC to DC conversions in this type of system. Now, usually there's no need for a critical loads panel in an off-grid system because there is no grid connection. all of the loads are on the main panel, and the only, incoming power to that panel is from your solar battery system. So since you're going to not have utility information here, you're gonna need to size this based off of a very detailed load calculation. So we'll talk about that and how to do those calculations in detail. But this is definitely a daily driver system. This is going to be sized for 80% depth of discharge. No ifs, ands, or buts about it. This is what the system could look like. So we're looking at an off-grid DC coupled solar array. Obviously, you don't have to have your batteries in cabinets, but again, they're not, our PHI batteries are not outdoor rated themselves. And so unless you're going to build some sort of a shed or put them indoors in a basement maybe, then you will need a cabinet for them. If you're looking at an outdoor install, you're going to want to check out our upcoming trainings on our new ESS system. So here's kind of a preview here of our ESS inverter. So as far as the sizing, this can be really fun. It's also pretty tedious. I'm not going to lie, this takes a long time to do. So something to probably factor into your bill for the customer. As far as loads calculations, you want to first separate all the base loads from the variable loads, as I call them. Base loads are going to be on 24/7. These are things that you need to account for the same amount of load daily, or maybe not 24/7, but they're going to be the same amount of load pretty much every day. So we're talking about security cameras, Wi-Fi routers, refrigerators, and in most cases, lights are pretty close to the same amount of energy demand every day. Things that are variable and maybe even possible to live without for a day or two, you're going to put on the variable load section. So I just separate these out for myself so I understand what's going on with the system. But things like the TV, washing machine, dryer, air conditioning, well pump, stove, water heater. Now, important to note here is that the water heater and dryer, I've put 0 consumption here. I've considered these to be gas-powered appliances. If they are not running on propane or natural gas, these are a large electricity demand here. Similar to the stove, it changes your whole system to be running air conditioning, a stove, a water heater, or a clothing dryer off of electricity. Not only does that increase your peak energy demand, but it also increases massively the storage capacity that you need to run those devices. So it's a good investment to make, but it is important to factor those into the size of the system. So you're going to add up all the power draw from all the devices, imagining they're all running at once, and this is the peak power demand. So, you maybe can talk to your customer and say, hey, as long as we're careful here to not run the stove and the air conditioner at once, we can decrease this by 2 kilowatts and go with a smaller inverter. That's always a possibility. So that's why I separate the variable and the kind of base loads. And you're going to need the energy demand added up of all devices. So to do that, take the power draw, multiply by the amount of hours they'll run that thing each day, and then you get the energy demand of that device. So in this example, when the customer has an 8.8 kilowatt peak power demand and 16.3 kilowatt hour need over the day, we can go with a 9 kilowatt inverter at minimum here, or 2 6 kilowatt inverters, for example, would do the same or better. You're always going to add 10 kilowatts, or excuse me, 10% to the energy demand in kilowatt hours to account for efficiency losses in the system. So that's 16, and a third is going to turn into 18 kilowatt hours needed in terms of storage, and you're going to size for 80% depth of discharge. So can anyone tell me how many PHI batteries you're going to need to power that system? I can't, raised hands won't help me. Just put your answers in the question and answer section. Awesome. Looks like everybody's getting this one. Glad to see your understanding what I'm talking about here. 6 batteries needed. All right. So some advantages of the Phi product, specifically SimpliPhi product, is when you're using it in off-grid, your customer definitely very commonly will need to expand that system over time. It is not uncommon to, have a customer add something to their quality of life. At first, they may start by living off-grid pretty simply, pretty affordably, with as little as they can get by with. And as they become more established or a little older, they're going to add loads to the system to live a little more comfortably. So that's a nice thing here, is you can add storage at any time as you need to, as the needs expand. It's a small building block, so this allows you to make a custom sized system, adding as little as 1 battery at a time. I've found that a lot of off-grid applications, transportation and weight can be a big factor here. You sometimes are traveling down to kind of a rough road, or maybe somewhere that's not paved. You sometimes need to carry the batteries downstairs or down a steep slope. Having that lightweight 86-pound battery that you can just carry with as little as 1 person, you can carry these up and down the stairs. I mean, I've swapped out 12 batteries for 12 new Phi batteries in a day, walking up 3 flights of stairs to do so and loading them into the back of my car. So it's definitely something you can do in a less straightforward and paved type of environment. So it's easier to maneuver these lightweight, smaller building blocks. It's easy to install them. Even if you're a one-man show, you can stack these up on your own. And the C/2 charge rate is something I want to highlight here. Is this allows for a large PV array size. So if you're in an environment where there's a lot of shade, a lot of trees around this property, and they don't get a good long time span for charging, they just have a couple of hour window in the middle of the day in the winter, then this allows you to oversize that PV array and charge the battery bank in as little as 2 hours. And it also enables a lot of multiple charging source scenarios. I don't think I've met a single person that lives on grid and has a residential wind or hydro setup, but I've met plenty that live off grid and have that type of setup in addition to PV. So it's something to consider, is that in the times where both PV and that wind or hydro system are producing, you're going to want a battery that has a fast charge rate. A lead acid battery, AGM battery, is not going to be able to handle a fast charge rate. Now let's talk about replacing an existing storage system. As far as lithium batteries, honestly, the specs are going to be pretty similar. So it's unlikely that you're going to have a massively different discharge rate. Just make sure you're matching the usable kilowatt hour, really the nameplate rating of the battery. Most batteries are going to offer that same 80% to 100% depth of discharge. Most often they're coming at 80% required for their warranty, some even as lower as 70 or 60%, but often you just need to match the nameplate kilowatt hour capacity of the battery. And then besides that, just checking the compatibility between your new battery and the equipment going on the system. So, or the equipment that's already on the system. So if you've got a communicating inverter that requires a communicating battery, the Phi battery is not going to be a good fit for that system. You're going to want to go with the SimpliPhi battery in that case. If you're replacing a lead acid system, there's so many more considerations here. lead acid depth of discharge is often as low as 20% to as high as 50%. So in general, if you've got a 5 kilowatt hour lead acid battery bank, you may only need a 2.5 kilowatt hour lithium battery bank. Just ballpark example here. I would recommend checking out our calculator really to go in depth here. But another thing is that the discharge rate of lead acid is so low. It's going to be maybe C over 20, C over 10, even C over 5 if you're really pushing them. And again, our lithium iron phosphate batteries are going for C over 2 easily, not even including the surge. So the discharge rate, whatever you replace your lead acid battery with lithium wise, the discharge rate of the lithium is going to be so much higher that that's something you won't even really have to think about. You just need to make sure you match the usable depth of discharge, the usable kilowatt hour capacity, I mean, after considering the depth of discharge. Now, another thing is equipment compatibility. Some lead acid systems are going to have old inverters and charge controllers that really are only made for lead acid batteries. Maybe they don't have a programmable low battery cutout, or as far as charge settings, maybe you cannot disable temperature compensation or equalization charges. So keep those in mind. Let's do a poll here. So remember, you want to match the usable kilowatt hour capacity. So if you've got 6 volt, 300 amp hour flooded lead acid batteries with 8 in a series string and then 2 strings in parallel, just as we see here, let's consider this customer is using 30% depth of discharge. So 30% capacity on each of these, and you've got 16 batteries in total. So do the math there and let me know how many kilowatt hours in total and how many kilowatt hours are usable. This is a hard one. Take your time. And remember, this is a 48 volt system with 6 times 8. 6 volts times 8 in series makes a 48 volt system. Crushing it, Kuno. Awesome job. So we've got 28.8 kilowatt hours here. And then if you multiply that by the usable capacity of 30%, so 30% of that amount of kilowatt hours is 8.6 kilowatt hours usable. Given that you're at 80% depth of discharge on the Phi battery, 3 batteries will actually exceed what these 16 can provide. This is why lithium versus lead acid replacements, the lithium replacement is always so much smaller and neater. One thing, another, point to remember though, going back to this lead acid system, if I can here, we saw all the wiring is daisy chained, one battery to the next. Now this is because they're in series. Not only will you not be able to connect our batteries in series, you don't want to daisy chain them even if they're in parallel. You want to connect to them such that they're all having an equal resistance between a common connection point. It's going to keep them well balanced. Just one thing to keep in mind. We have plenty of videos on our wiring techniques more specifically. I just wanted to point this out today very briefly. Again, this is not a correct wiring method. Daisy chaining lithium batteries would result in imbalances, and over time, that's going to wear down one battery more than another and just do damage. So that's all I had today. Please hit me with all your questions. Got a couple minutes remaining here. And great job, everybody, with the polls. We did not have one wrong answer today, so I must have been doing a good job. All right, I'm going to give it one more minute here. Got a good question here. What would be the usable capacity of the new SimpliPhi 4.9 battery at 80% depth of discharge? So what we're going to do is we're going to multiply 4.99 kilowatt hours, which is the total capacity, by 0.8. We're going to get 3.992, which is about 4 kilowatt hours per battery. So that's the usable capacity if you're cycling our new 4.9 kilowatt hour battery daily. Awesome. That's the only question I have here. So I'm going to call it a day. Thanks everybody for hopping on today, and I will see you next time.